how many bits do we need to represent anything from negative 16 to 16?
5.
5 or 4?
5. Include the side bit.
Okay. You need to take, okay, all you have to do is 15.999999999, okay? Okay? How do you get 15.9999999? So I need 1111, which is 15, right? And then, guess what? I need a lot of 1 here, right? That's how I get 9999999, okay? So I'm gonna throw away all the 1 here, okay? Oh, well, I need a sign bit here as well. Okay, so you're right. I need 5 bits. 1, 2, 3, 4, 5. Okay, I need the sign bit plus the 4. Okay, and then I'm gonna throw away these 2 guys as well. Okay, so I only keep 3 bits. The sign bit plus the 2 guys. Okay, now let's think about. So where is it right here? What is the first? How do I get 0 out? How do I get 0 out? I need the sign bit to be 0, right? And I also need 0, 0, right? Okay? So what is the maximum number that I can represent if it's 0, 0, 0 here? 1, 1, 1, 1, 1, 1, like this, right? So what is this? 3.999, which is roughly 4, right? So this is 4, and this is negative 4. Agree? So that's 4 and negative 4. Not including 4, okay? Excluding 4, excluding negative 4, but that's how I get 0 out. That's how I get 0 out, okay? How do I get 1 out? It would generate a lot of 0 for us, right? It would generate a lot of 0 for us. And that's why this is very effective in compression. It generates a lot of 0 for us. Okay, so this is called a double dead zone. Dead zone means you fall into the dead zone, you get 0. You get eliminated. Okay, you will never survive. Okay, so this is a double dead zone quantizer, and so this is fine. How do I put the reconstruction point? How do I put the reconstruction point? Well, in the middle is one way, right? But the optimal way is what? We observe the PDF of x, right? And put the midpoints accordingly. Okay? So that's the optimal thing to do. Now, if you choose the midpoint reconstruction, which is usually a pretty reasonable thing to do at high bit rate, okay? Then the midpoint will turn out to be the red dot or the reconstruction. Okay. Now, if I have the red dots, I'm going to show you if let's say I want the midpoint as my reconstruction. I'm going to show you very quickly how we can inverse quantizers in a very smart way. Okay? So let's take this original symbol. Suppose that x coming into the quantizer has value 22. Okay? So 22 is 1, which is the sign bit. Okay, I don't have a sign bit now. Okay, so I just ignore the sign bit. Okay, so let's ignore the sign bit. So this 22 is 1, 0, 1, 1, 0. Okay? Alright? Now, if I throw away the 4 bit lanes, okay? If I throw away the 4 bit lanes, then I only keep 1 plus the sign bits up here, okay? Then, so in the decoder, you receive 1 bit at a time, right? You receive 1 bit at a time, and the first bit you receive is 1. You haven't received these, okay? You receive the first 1 bit. Can you reconstruct? What do you mean no? What is, okay, suppose that I receive 1 and then my communication line gets cut off. I have to reconstruct now. What am I going to do? Okay. Can I think what is the range? Okay, if I'm a smart decoder, right? I receive a 1. Is there anything that I can say about the behavior of X? It lives from where? 16 to 32. Right? Is that a good guess? It's not a guess, it's true, right? I receive a 1. Okay? So I know the range is anywhere from 16 to 32. I don't know exactly where, but I can tell you that's the range. Okay? I can tell you that's the range. So if I have to reconstruct now, what would I do? The midpoint, right? Okay? Suppose that I don't know anything about X, okay? I'm blind, okay? And I'm trying to make reasonable guess. I'm going to guess the reconstruction is in the midpoint of 1632, which will turns out to be 24. Agree? Now, let's take it one step forward, okay? After we receive that 1 bit, our communication channel opens, and then it leaks us another bit. Give us 1 more bit, okay? So it gives us 1 more bit, 0. Okay? What can I say? And this is called the refinement bit. Refinement means you update. Okay? So I receive another 0. What is my range now?
16 to
it's still 1632, correct? Okay? But then since I receive a 0, I'm going to be able to guess that it's in the lower half. It's in the lower half of 16 and 32. Right? It will be in the lower half. It cannot be in the upper half. If it's in the upper half, I should receive a 1. Correct? Okay? So I'm going to be able to guess that my range is now 16 to 24. And if I suggest the midpoint reconstruction, that's going to be 20. That's going to be 20. Okay? Now, this is interesting. Take a look at 20. 20 is 24 minus 4. 20 is 24 minus 4. Minus because I receive a 0. If I receive a 1, what is it going to be? Plus 4. So it becomes 28. And again, that's the midpoint of the upper range. Okay? So see, this is called a refinement quantization. Because the more bits you receive, okay, the more refinement that you're going to be able to do. And guess what? We're coming closer and closer to 22. Eventually, we're going to hit 22. Okay? So the next step is I receive another 1. I receive another 1, which will, so I'm going to be able to say that this range will be the upper part of 16 to 24, which will put me at 20 to 24. Put me at 20 to 24. The midpoint is 22. The midpoint is 22. And I get 22 by taking this 20 right here. I add 2 to it. Okay? F4 or F2 depends on where you are. Okay? Add 2, add 4, add 1, add 8, minus 8. It depends on where you are on the bit plane. Okay? So you must know where you are. So I'm making an assumption that I know where I am right here. Okay? So the encoder has to tell the decoder that this first bit lives on the 5th bit plane or something. And that's how you can do this entire process. So this is called embedded quantization and embedded inverse quantization. The way that you do quantization is simply sending 1 bit at a time. You take this and you send 1 bit at a time. First you start with a sign, and after that you send the most significant bit, the next most significant bit. You keep on going until you run out of bit rate. Okay? At the decoder, this is what happens. Okay? Okay, so you can wait until this guys get here, or you can do reconstruction 1 step at a time, like this. Okay? So in this case, we get lucky, right? I don't need the last 2 bits and I already get 22. But I get lucky. I don't always get lucky. Okay, sometimes we get lucky. Okay? And that is you can show that this bit plane truncation idea or embedded quantization is actually just a scalar quantization with step size delta being equal to 2 to the n. And then the middle step size is twice this large. Okay, this is being used in JPEG 2000. We will revisit this guy in the second part of our lecture in a few minutes. Okay, before we take a break, I'm going to just spend 1 minute talking about something we call vector quantization. Okay, so what we have been talking about so far is for scalar quantization, meaning that one guy coming in, one guy coming out. Okay, vector quantization is an n-dimensional generalization of scalar quantizer. So instead of one guy coming in, you have two guys coming in, two guys coming out, so on and so forth. So you are doing grouping, okay? So if you do 1, 1 like this, then if you have two guys, x1, x2, follow, concatenate two guys, one after the other, so we can call this separable scalar quantizer. That means we put all the midpoints right at the nice grid, okay? But if I have a two-dimensional signal, and I want to do two guys in, two guys out, then you will be able to do something like this, okay? Which definitely should be a lot more effective in terms of the trade-off between bitrate and reconstruction errors. Okay, because over here you are forced to use square. You cannot use anything else except square. But over here you can come up with other geometrical shapes. Okay, now. Vector quantization is supposed to be an improvement over scalar quantization. However, with entropy coding following up quantizations, then it doesn't turn out to give you a huge advantage anymore. Okay, it turns out that the advantage is pretty small. So that's why in practice, all you see is scalar quantizer. You rarely see vector quantizer except in the academic environment, where people are actually interested in mathematical result rather than practical implementations. It should be a lot more difficult.